Hello students, welcome to engineeringtalks.com. In this video, we will go through the stress strain diagram of mild steel. Mild steel is a low carbon steel. It is a ductile material. So in this lecture, we are going to understand the physical meaning behind every region of the stress strain curve of a ductile material. So what do you mean by a ductile material? Ductile material can be defined as a material which exhibits large reduction in cross-sectional area and high degree of plastic deformation before fracture. And the property by which these materials exhibit this large reduction in cross-sectional area and high degree of plastic deformation is known as ductility. So how can we classify these materials as brittle and ductile? Based upon percentage elongation. Percentage elongation is given by the equation final length minus initial length divided by initial length into 100%. If percentage elongation is less than 5%, we can classify such materials as brittle. If the percentage elongation is anywhere in between 5% and 15%, we can call such materials as intermediate ductile materials. If the percentage elongation is greater than 15%, such materials are highly ductile materials. So these are highly ductile materials. So here in the case of brittle materials, you can see that the percentage elongation is less than 5%. So percentage elongation is very less in the case of brittle materials. So these materials exhibit very less or no plastic deformation before fracture. These materials break without any warning. So for plotting the stress strain curve or stress strain diagram, we will be conducting a test known as tension test or tensile test on the specimen. And this test will be conducted using a machine known as Universal Testing Machine or UTM. Here I have shown a universal testing machine. This machine is known as a universal testing machine because this is not only used for conducting the tensile test, but also for conducting various other tests like compression tests, shear tests, etc. So we will be able to analyze various material properties under different types of loading. For conducting the tension test, the specimen that we'll be using looks somewhat like this. As you can see here, this specimen has larger diameter at both its ends. And here there is a length over which the cross-sectional area is uniform. So before conducting the test, what we'll be doing is, we will be measuring the initial diameter of this specimen and we will be measuring the initial length of the specimen. And that length will be the gauge length of the specimen. So how do we measure the gauge length of the specimen? We punch 2 points here like this and we measure this length as the gauge length. The length between these 2 points will be taken as the gauge length. Let us call it as L0. So L0 is the gauge length and D0 is the initial diameter. Now, this specimen, when you look at the specimen, the shape looks somewhat like a dumbbell, right? So the specimen is also known as dumbbell shaped specimen. It has another name as well, that is dog bone shaped specimen. Now for conducting the test, this test is also known as uniaxial tensile test. For conducting the test, we will be mounting the specimen in between the two grips or jaws of the universal testing machine like this. These are the jaws or grips of universal testing machine or UTM. For mounting the specimen in between the two grips, we have provided larger diameter at both the ends of the specimen. The part over here, this one is the upper crosshead. This one is the movable crosshead. After mounting the specimen in between the two grips, the machine increases the separation between the two grips or jaws according to prescribed testing condition. In the case of crosshead control test, for example, machine may be instructed to increase the crosshead separation at a specified rate, thus stretching the specimen. What happens if this crosshead moves down with respect to this one? This specimen, since it is fitted in between these two grips, it will start to get stretched, right? It will start to get elongated. An important point to note here is we often casually say that we apply tensile load to the specimen. Physically, that is true. The specimen is subjected to tensile loading, but experimentally, we should be able to distinguish between what the machine controls and what the specimen responds with. So here, the machine increases the separation between the grips, thus stretching the specimen. So the deformation is imposed on the specimen. Against this deformation, there will be a resisting force induced within the material, within the specimen, right? That induced force, that resisting force will be measured by the load cell and indicated by the load indicator. This is the load indicator. So we are imposing the deformation and we will be noting down the response, that is the resisting force, the force induced within the specimen against the deformation. And the extension of the gauge length can be measured using extensometer or any other suitable strain measuring system. The immediate result of the tension test is not the stress and strain values. Then what will it be? It will be the resisting force F and elongation delta. As we stretch the material, as we stretch the specimen, we obtain the resisting force as the response. From this elongation of the specimen delta L, we can easily calculate the strain epsilon, and from this resisting force F, we can easily calculate stress sigma. What is stress? It is nothing but the resisting force per unit cross-sectional area. For calculating the stress, here we will be considering the initial cross-sectional area A0. As we stretch, as we elongate the specimen, we know that the cross-sectional area reduces. But here we will be considering the initial cross-sectional area and not the instantaneous cross-sectional area. The stress obtained by considering the initial cross-sectional area is known as the engineering stress, sigma E. So sigma E is nothing but the engineering stress. So here we will be considering the initial cross-sectional area throughout for calculating the stress value. And strain can be easily calculated using the equation delta L by L naught. So here also we are considering the initial length, that is a gauge length, right? So this strain is nothing but the engineering strain. So epsilon E is the engineering strain. We are not using the instantaneous length for calculating the strain value. For calculating the strain value, we will be using the initial gauge length. Because as we stretch the specimen, the length increases. So instantaneous length varies from point to point, but we will be considering the initial length. What if we use instantaneous area and instantaneous length for calculating the stress and strain values? Then we will get the true stress and true strain values. So true stress and true strain can be calculated using the instantaneous cross-sectional area and instantaneous length. We will go through the true stress and true strain in the upcoming videos. In this video, let us focus on the engineering stress strain diagram. So we will be straining the material and we are getting the resisting force as the response. So we will be plotting the strain values along the x-axis and stress values along the y-axis. Now we understand that this is not just stress strain curve, but engineering stress versus engineering strain diagram. Keep that in mind. So now it's time to go through various regions along this engineering stress strain curve. Let us mark a point over here. As we start stretching the material, as we stretch the specimen, what happens is atoms in the crystal lattice, they start to get slightly displaced from their original equilibrium positions. But the interatomic bonds resist this deformation. Then what happens? The stress starts to increase. So here in the initial portion of the curve, you can see that the stress is getting increased, right? Stress is increasing, strain is increasing, and we reach a point, let us call it as A. This point A is the proportionality limit. This A is the proportionality limit. So this portion OA of the curve, this is a straight line portion, right? Here, stress is directly proportional to strain. Within this limit, stress is directly proportional to strain, and hence A is known as the proportionality limit. So here we have stress sigma directly proportional to strain epsilon. If we want to remove this proportionality sign, we have to introduce a constant of proportionality. That constant of proportionality is denoted by capital E. So sigma is equal to capital E epsilon. And this E is the Young's modulus of the material. The constant of proportionality is the Young's modulus of the material. This Young's modulus of material is actually a measure of stiffness of the material. A steep slope means high value of Young's modulus, which indicates greater stiffness. So if we take a slope of this line, tan theta, if we take the slope of this line, we get the Young's modulus of the material. So slope of this portion gives us the Young's modulus of the material. Now, after stretching the material, if we release the tension, then these atoms, they return to their original positions, which means that the specimen regains its original shape and size. So the material behaves elastically within this region. So this is not just a linear region, this is a linear elastic region. So OA is linear elastic region. The material behaves elastically here. Now, if we further stretch the material, what happens is the straight line portion, it becomes a little bit curved and we reach a point B. The linearity is lost. It is no longer a straight line. The linear relationship between stress and strain is lost. But the elasticity of the material is still there. This point B is known as the elastic limit. So within this limit, the material behaves elastically, which means that if we release the tension from the specimen, the material regains its original shape and size. That is, the material comes back to this point O through this line. It comes back to O through the same line. But if we stretch the specimen beyond this point B, the material enters the plastic zone. So up to point B, it is the elastic zone. And beyond point B, it is the plastic zone. So if we stretch the specimen beyond point B, and if we release the tension, then what happens is there will be some amount of residual deformation in the specimen. Suppose after reaching this point, if I release the tension, then the specimen, what happens is it comes back through this line and it reaches here. So here you can see that still there is some amount of strain, right? This is residual deformation. So this is the residual deformation. So there will be some amount of deformation in the material even if we release the tension. So that is permanent plastic deformation. Up to point B, the material behaves elastically. So up to point B, we have the elastic zone. After point B, it is the plastic zone. Material starts to plastically deform. Upon further stretching the specimen, the stress, it continuously increases and it reaches a point over here. This point, we can call it as C. After C, we can see a sudden decrease in the stress value. There is a dip and it reaches a point over here. We can call this point as C prime. Once it reaches C prime, we can see that there is significant amount of plastic strain here, but the stress is almost constant. The stress remains constant at C prime, but the deformation, it is actually increasing. The plastic deformation is increasing. So we have a large amount of plastic deformation here at constant stress. Okay. Now this point C is known as the upper yield point. And this point C prime is the lower yield point. Now let's understand what is happening here actually. In metals, plastic deformation happens mainly due to the movement of dislocations. Dislocations. So what are these dislocations actually? Dislocations are line defects present in crystals. There are different types of defects in crystals. Dislocations are one of them. For now, you just have to understand that dislocations are line defects in crystals. In steel, the interstitial atoms like carbon, nitrogen, they diffuse to the regions near these dislocations and they gather around, they cluster around the dislocation, forming something known as coronal atmosphere. So these interstitial atoms form coronal atmosphere around the dislocations and they pin the dislocations. They hinder the movement of dislocation. So a high value of stress will be required to break this coronal atmosphere so that the dislocations are free to move. So as we further stretch the specimen, we reach a particular value of stress here at point C, that is the upper yield point. Once we reach the upper yield point, there is enough stress to break this coronal atmosphere. So dislocations will be able to unpin themselves from the coronal atmosphere and they are now free to move. Once they are free to move, now that much resistance is not there within the material. So the stress value reduces. So that much amount of stress is not required to bring about the plastic deformation. Since the dislocations are free to move, we can get plastic deformation at significantly lower value of stress. So here we can see a dip in the curve from C to C prime. So from upper yield point to lower yield point, there is a decrease in the value of stress. So from lower yield point onwards, we can see a significant increase in the plastic strain. But the stress remains almost constant at lower yield point here. So here we have significant plastic strain, right? So this process by which the material undergoes significant plastic deformation at relatively constant stress is known as yielding. And this region from C prime to this point, let us call it as D. There is no particular name associated with this point, but let us call it as D for now. So this region between C prime and D, this horizontal portion from C prime to D is known as yield plateau or Luder's band propagation. So C prime D is the yield plateau or Luder's band propagation. So what's happening here? The plastic deformation, it doesn't occur uniformly throughout the entire specimen at first. Instead, what happens is localized regions of plastic deformation start to develop in the form of bands, and those bands are known as Luder's bands. So Luder's bands can be thought of as regions where the material has already yielded and the plastic deformation is propagating through the gauge length. So in the yield plateau, what is happening is the plastic deformation, it is getting propagated through the entire gauge length. The bands start to develop. These bands can be thought of as regions where the material has already yielded. These bands develop at approx 45 degree to the stretching direction. Now, in the nearby areas, the material is still unyielded, right? So what happens is the plastic deformation starts to propagate. Luder's bands propagate throughout the entire gauge length. And by the time we reach this point D, the plastic deformation would have got propagated throughout the entire specimen, that is the gauge length. And now the material enters the uniform plastic deformation. After this point D, another mechanism becomes increasingly important, and that is known as strain hardening or work hardening. So what is strain hardening? During plastic deformation, what is happening is number of dislocations and their interactions increase. These dislocations increasingly interact, entangle and obstruct each other's motion. And now the movement is difficult. So progressively higher value of stress will be required to bring about further deformation. So here you can see that the stress value starts to increase. And finally, it reaches its maximum value at point E. This point E is the ultimate tensile strength. This is the maximum value of stress that the material can withstand before fracture. So this is ultimate tensile strength or UTS. Between the points D and E, the material begins to harden. The material becomes harder and stronger. Hence the name strain hardening or work hardening. So this region DE represents strain hardening or work hardening. Okay. Now we have reached the UTS, the ultimate tensile strength. This is the maximum value of engineering stress reached by the specimen, and this corresponds to the maximum force response measured during the tension test. Now at UTS, necking begins. Necking begins. So what is this necking? The plastic deformation, it starts to get localized over a particular region. What happens is, in that region, the cross-sectional area starts to reduce. So the cross-sectional area in this region, it begins to reduce more rapidly than in the surrounding regions. And this localized reduction in cross-sectional area is known as necking. Once necking begins, a positive feedback process develops. As the cross-sectional area at this particular region decreases, the local stress over here increases. This promotes further plastic deformation at the same particular location, causing the cross-sectional area over here to decrease even more. Then what happens? This leads to increase in the local stress again, and this process continues. So the plastic deformation becomes more and more concentrated over this region, leading to the formation of neck. As the process continues, a crack eventually develops, and this leads to the fracture of the specimen. During the process, the load-bearing capacity of the specimen reduces due to the rapid reduction in the cross-sectional area. Since the engineering stress is calculated based upon the original cross-sectional area, the curve starts to reduce. And it finally reaches a point, let us call it as F. This point F is the fracture point. The specimen finally fractures or ruptures or breaks. So this is known as fracture point or breaking point or rupture point. Between the points E and F, in the region between the points E and F, we have necking. So EF represents necking. And the stress corresponding to this point E is the ultimate tensile strength. So that is sigma UTS. And the stress corresponding to this C prime is the yield strength sigma Y. For designing the structural components, we usually use the yield strength as the strength criterion because permanent deformation may make the material unusable long before it actually breaks or fractures. For example, a steel beam supporting a machine. It might not break, but if it permanently bends, then the component has failed to perform its intended function, right? So yield strength is usually taken as the strength criterion for designing the structural components. And here, as you can see, in the case of mild steel, we have distinct upper yield point and lower yield point. In the case of materials with a distinct upper yield point and lower yield point, we usually take the lower yield point as the yield strength because the upper yield point is the value of stress associated with initiating the yield process. Once the yielding starts, the stress value suddenly drops to the lower yield point and the material continues to deform at approximately constant value of stress here at lower yield point. So this C, that is the upper yield point, can be considered as a transient peak associated with initiation of yielding. Once the yielding starts, the stress drops to the lower yield point and the plastic deformation continues there. So we usually consider the lower yield point to be the yield strength. So this is the engineering stress strain curve of mild steel. If you found this video helpful, please like the video and subscribe to the channel for more videos like this. In the next video, we will look at different material properties that can be obtained from the engineering stress strain curve. We will also see what true stress and true strain mean and how they are calculated and how they differ from the engineering stress and engineering strain. So make sure you watch the upcoming video. Thank you for watching.